Okie dokie. So here is an explanation of question number 62 from our homework for week 3. 3 equals our week. There are a lot of students asking about this. So here it goes. We have this situation, there's a diagram, somebody is jumping or stepping horizontally out of a window, and the fire people down here are going to rescue them. So, person jumps out of a 4th-story window 18 meters above the firefighter's safety net. So it's 18, this diagram is good. 18 meters above where the net is unstretched. Survivor stretches the net 1 meter before coming to rest. So they're speeding up over the course of 18 meters and then slowing down over the course of 1 meter. So we expect their acceleration while slowing down to be much greater than their acceleration while speeding up. And we know their acceleration while speeding up, it's assumed that they are on Earth. We know their acceleration while speeding up is 9.8 meters per second every second in the downward direction. So, we want to know what was the average deceleration, and deceleration, sometimes we use that word, but deceleration experienced by the survivor when she was slowed to rest by the net. So what's her acceleration here? And we know her acceleration here is going to have a positive value because she's losing downward velocity. What would make you do safer? Yeah, okay, so that's sort of a qualitative question. But for part A, I know it seems kind of out there, like how on earth are we supposed to know that based on the information we're given? So the first step is to actually write down, try to draw a diagram, all that stuff. So here's what I would like to see. Forget about what's in red right now. But what I would like to see when you're solving this is you're reading through the question and you're writing down information. We're getting used to these variables and what they mean, and then you have a diagram. So here's my diagram. They're falling 18 meters. I have these, I will zoom in. We have these arrows to indicate the person's speeding up. I have this as kind of the 0 point, and then this to remind me that she'll be slowed down by this net. Okay. At the top, so initial velocity, she's just stepping out of the window, and so her initial velocity is 0. We don't know how fast she's going when she hits the net, but because we're looking for how much, well, her acceleration, the rate at which she slows down, we do need to know how fast she's going. So this is a 2-step process. So her initial position, initial position at the window is 18 meters. Her final position once she hits the net, so we're defining, for this first part, we're defining the height up here, or the position, as 18, and the height or position right here as 0. If you wanted to, you could define this as 0 and this is negative 18, and the math is going to work out just the same. Her acceleration is negative 9.8 because she's on Earth. And initial velocity, she doesn't jump up or throw herself down at the net. Her initial velocity in the vertical direction is 0. And we want to know, so I write, well, what do we want to know with a question mark? Okay, so this, I don't see students doing this normally, and this is really helpful. I know it seems like a lot of work, but trust me, it will help you organize your thoughts. So we have all this given information. We know what we want to know. Notice how time, we don't know how long it takes, and we don't need to know how long it takes. So time isn't even mentioned. So, you know, the question I also hear in physics class is, well, what formula do I use? And first of all, I want you to actually think about it and that kind of thing. But when you are sorting, you're looking through the formulas, this formula involves what we want to know, what we do know. Notice how it doesn't involve time, so this would be sort of a good choice for the formula to use. So we're looking for final velocity. Initial velocity is 0. Acceleration, notice how I put it in negative, right? She is accelerating downward. And notice how this term is displacement. I'm going to write that. Displacement, sorry, that's a little messy, but I know this whole x sub 0 and x can get confusing. Know that this whole term is displacement, and so notice how we get a negative 18 meters as her displacement because she is moving downward. She ends up below where she starts. So if we solve this for v, we end up with 18 point, notice how I used all these decimal places? That is, I'm ignoring the significant figures for now because we're going to use this later in the calculation again. So I'm not rounding until the final answer. I have an arrow here to indicate direction. If I had put a negative in front of the number, that would mean the same thing. I'm trying to stay organized by writing units. So that's the speed she's going when she hits the net. How fast is that? Remember, meters per second to miles per hour is approximately double. So we could say, 18, 19, 38. It's probably about 40 miles per hour, just to give you a feel for what does that mean. All right. So an 18 meter, that's almost 60 feet. She'd be going fast. All right, so that's going to hurt if she doesn't hit the net. Then, when she's slowing down, and I'm sorry, I'm going to go back. If you're really confused, you should actually write out the units here. This is kind of shorthand, but I could have written meters, meters, meters per second squared, meters per second, and meters per second. And while you're getting used to the units and the quantities involved in physics, that might be a really good idea. So, we know how fast she's going now, 18.78, blah, 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 blah. And she hits the net and slows down. So let's see. Right over here, for the slowing down part, I wrote out, we know she's traveling this fast when she hits the net. And so there's the net. This is where she drops to. So she slows down over only this small distance. We know her final velocity after she slows down is 0. So this right here, I'm going to highlight. This is frequently hidden information. So the question will tell you something, and you're like, it's not giving me information, but you know that the thing is slowing down, or is slowing down to rest, or starts from rest. So in this case, our final velocity is 0. In the case above, our initial velocity is 0. And the question did not explicitly state that. You just had to understand that from context. While she's slowing down, okay, she has velocity in the downward direction. Her acceleration is going to be in the upward direction. This is what we are looking for. So I have defined her initial position. So I'm saying, all right, that is a height of 0, in which case her initial position is a height of 1. So notice how, once we know how fast she's going, I'll write a little arrow, we're completely disregarding all that information from the first part of the question. Okay, forget about the building. All we're looking at is slowing down in the net. So we're defining the bottom as 0, and then the height of the net as 1. Again, you could have defined this as 0 and this as -1, and you'll end up with the same thing. So, looking at this, it looks like we have and want to know the same information as when we solved above, meaning use the same equation. Notice how time appears nowhere. Don't know it, don't need to know it. So if I substitute in her final velocity when she comes to rest and the net is 0, her initial velocity when she hits the net is 18.78, and I put all those decimals into the calculation. To A, so we're not talking about gravity, we're talking about the net slowing her down, and then displacement ends up being -1. So this is quite a large acceleration. I think the question asks something about how many G's is that? G's. And so we know 9.8 meters per second squared. We say this is 1 G. This is this letter variable G we use to represent the acceleration due to gravity. So, if you become an astronaut or an Air Force pilot or something like that, you have to undergo training where they basically put you in this human centrifuge and spin you around until you pass out to see how many G's of acceleration you can withstand before you vomit or pass out or can't control a plane. So to figure out, I know it sounds fun, to figure out how many G's 176 meters per second squared is, we could just divide, and I think we end up with something like, that's approximately 18 G's of acceleration. So that would hurt. Thanks for listening.